We are, yes. Well, we were. And then it bumped you. Try one more time. It bumped you out there for a second.
All right.
We had it there for a second. Here it comes. All right, we got you.
All right, you got me now?
Yes, sir.
All right, sorry about that. I've been used to so many different of these web-based applications. They're all a little bit different. So anyway, guys, really happy to be with you this morning. My name is John Engberg. I'm the Vice President of Engineering here at Barnhart out of Memphis. And I went to Mississippi State. I got a degree in civil engineering. And so my background is more in the structural steel design, is kind of my background, what my experience is in. And what we do at Barnhart, I don't know, some of you may know about what we do, probably you don't. It's a fairly specialized field. And what we do is we move heavy equipment, we move heavy stuff for large industries. So a lot of the work that we do is in power generation type industries. So working at power plants, at nuclear power plants, fossil power plants. We do a lot of work in steel mills and heavy industries like that have large components that have to be replaced from time to time. So that's kind of just a quick overview of who I am and a little bit about what Barnhart does. So again, this is just kind of outlining who we work for, who some of our customers are. Like I mentioned, a lot of work in the power industry. We do a lot of work at refineries. So the locations where they refine, crude oil and turn it into gas and jet fuel and kerosene and all that good stuff. We do a lot of work in those facilities. We do a lot of wind construction. So you hear a lot of, that's a big industry right now that the government likes to subsidize is these wind turbines that produce power. And we do a lot of work erecting new wind turbines and maintenance of existing wind turbines. The blades break, the gearboxes fail. Sometimes they catch on fire and we have to take them down with them in some state of damage. So that's something that we specialize in. And another cool industry that we work in is called Accelerated Bridge construction. And I've got some pictures here at the end of the slide, and I'll kind of go over a previous job that we did. And basically what that is our nation's infrastructure is getting old. A lot of these roads and bridges that were built 50, 60, 70 years ago, some of them, and they need to be replaced. They don't last forever. And obviously we as society don't like to be inconvenienced by shutting down a bridge for a year to rebuild it. And so we've come up with not Barnhart, but the industry, engineering in general, has come up with a way of building a new bridge on the side of the road. And that takes months to do, but the road is still open. And then we come in there over a weekend with some of our specialized gear, and we'll come in there and lift the old bridge off of the abutments, take it to a laydown area, stage it on some temporary shoring towers, go back and get the new one and set it down. And we can do that over about 24 to 48 hours over a weekend, and have it back up and running for traffic by Monday morning. So that has a lot of advantages. Obviously, the impact to the traveling public is reduced, and it's also, that's not the only impact, but it also affects commerce and the economy and everything like that, being able to keep those roadways open. So we'll touch on that in a little bit, but this is kind of some of the areas that we work in.
Hey, Mr. John,
all right, as far as how engineering plays,
what you described is That's one of the coolest things I've ever heard. So you're literally building a bridge to the side of the bridge, and then you lift it up and put the other bridge there. I've never thought of that. That's amazing.
Yeah, we do it a lot. We do it a lot up in the Northeast area for a couple reasons. One, the population densities and the traffic counts are so high up there, and number two, it's got some of the oldest infrastructure in the nation, and so the demand is the highest right there. But we've actually done it. We've done it in other parts of the country. We had a job here in Memphis last year where we did a similar type construction technique. And we've done it, it's becoming more prevalent with the Department of Transportation. They're starting to see the value and starting to pick up on it. So it is somewhat new. And so anything, it takes a little bit of time to catch some, to get steam and get some support and buy-in from all the different stakeholders. But it is definitely something that, you and I as the traveling public can appreciate, not having to be inconvenienced with that for months on end. All right, so kind of getting into how engineering supports and how engineering plays into this line of work. This is something that y'all are really kind of have an advantage, because I would have loved to, when I was y'all are in what, 8th grade? I would have loved to have had somebody tell me that this was an opportunity at that stage of my life. I didn't figure out what I still don't know what I want to do, but you're always being exposed to new opportunities and new things that pique your interest. And that's what it's really all about, is finding out what is it in life that you're passionate about, and then go find a way to make a living at it. And so, to me, this is really cool from an engineering standpoint, that we get to be part of these projects and get to use, the math that you're learning right now. We use it every day. It's just part of our life. So it is important what you're learning right now. So this is kind of what we do from an engineering standpoint. Everything that we do is highly planned. That's why engineers have a job at Barnhart, is figuring out the plan. And so part of that is drawing it out, laying it out, making sure things fit, seeing how the equipment lays out with the site that we're working in, or the any obstructions that can't be moved. So just kind of laying things out and make sure they fit from a kind of a spatial standpoint. And once we get the equipment laid out, then we have to make sure that the equipment can support the loads that we're going to be, putting on it. So we've got to do calculations to determine what are the loads, what are the reactions down to the supporting surfaces that our gear is set up on. The loads going through our equipment, is it within capacity, or are we overloading something? Being able to predict deflections of beams to know how much they're going to be deflecting under load, and is that going to be acceptable, or is that going to cause a problem? We're dealing with massive loads. We're dealing with anything from, we deal with smaller stuff, 5,000–6,000 pounds, but we deal with things all the way up to over 4 million pounds sometimes. And so the loads are very extreme, and you have to make sure that you understand how the system is going to respond under load. So it's one thing to know, does it have the strength to support the load, but also, is the beam going to be deflecting 5 inches? Is that acceptable, or is that going to cause things to kind of slide down the hill as that beam deflects? So that's why the calculations are so important, is to understand how the system's going to respond. Some of these other bullet points, we've got about 50 branches across the country, and not all branches have engineers. They're local. And so my engineering team here in Memphis, we serve all those branches. So if they get a project that needs engineering, they call us, and we're basically a kind of an engineering consulting firm, internally to Barnhart for those branches. We take all the high complexity jobs, which I'll show some of those here in a little bit. We provide technical oversight. So again, having that engineering and technical background, we understand from a technical aspect aspect where the high risk points are in the work, and we're able to help our field crews out by keeping them abreast of the situation when it comes to a technical type issue versus just an operational, using the equipment type consideration. We also develop our own engineering standards. I mentioned what we do is very specialized, and so if you're going to build a house, there's building codes out there that you have to build the house in accordance to that. If you're going to build a car, there's standards, there's national standards that you have to design it and build it to those standards. Well, a lot of what we do doesn't have a national standard, and so we have to develop our own based on experience, based on good sound engineering judgment, and so that's part of the job as well. And then training new engineers, training our people, and risk managing the jobs out there in the field. So, oops, sorry about that, went the wrong way. So here's kind of an example. We've got several different types of work. We've got cranes, we've got lift towers, we've got heavy haul, we've got, we're rolling pieces of barges. So this would be an example of transporting. This is a steam turbine to a power plant. And so this is an over-the-road type transport configuration. You can see there's hundreds of wheels underneath these trailers, and the whole name of the game in the heavy lift and the heavy transport industry is spreading out the load. You spread out the load until whatever you're driving over or bearing on can support that load. And so that's what these trailers do. They've got, they're modular, so you can connect them together as long as you want. I mean, obviously there's practical considerations that come in where you can't make turns if you get it too long, but you can connect them together and make them, shorter or longer depending on the loads. And in this particular configuration, we've got two separate trailers. And so they're able to kind of steer and pivot independent of one another. That makes the rig more maneuverable, where you can get down the road and make turns. Whereas if you had one continuous trailer, well, now you got a trailer that's 250 feet long, and making a turn can be kind of problematic. So we've got this specialized equipment. So engineering plays into, all right, the span of these girders here. Can you see my mouse?
We can, yes, sir.
Okay. So the span of these girders right here, the longer that gets, how much does this piece weigh, and are those girders, can they support the load, or do we need to do something different to get those girders within capacity? That load comes back down to the trailers. So, half the load's going to go this way and load up this trailer. The other half's going to go to the front trailer. And then we have to evaluate the trailers for the loadings on them. So there's other things, other considerations, but this would be an example of, for an over-the-road heavy transport type project. This would be the drawing that all the engineers would, work on, and this is kind of their deliverable to the customer, to the field crews. All right, so the other aspect of what we do, this is a different type of project. This is what we call an MLT, or a modular lift tower, and it's a temporary lifting system. So basically, it's an erector set is really what it is. Everything kind of pins together. You can make it as tall as you want, different width based on what you're trying to do. But this type of drawing just kind of shows how the equipment is going to be laid out. Again, making sure that everything's going to fit. We can send this to the customer so they understand what it's going to look like when it shows up on their site, how it's going to impact their site, and it shows all the details for our field crews so they know how to assemble the system. This is the next set of drawings, the erection sequence. So again, show the layout. How does this thing go together? What if there's certain points in the erection where we have to stop and do something critical? We'll call it out on these type of drawings. And then the sequence drawings for the actual lift. What is it going to look like? So in this case, there's this big vessel. This was at a refinery up in Washington State, north of Seattle. And this piece needed to be, it came in horizontal, and it needed to be stood up vertical, and then indexed over to set it on the anchor bolts in the
what
plant.
Did that weigh?
This weighed about I think it was about 600,000 pounds.
So a little over half of a million pounds, and you had to lift it vertical and then raise it up.
Yeah, so we had the back end down here supported by the trailer. The head of it was supported by what we call a strand jack. It's just it's kind of a hoist, but it provides the vertical lift. And we started lifting the head end, and as we lifted the head end, the trailer would drive forward, and it would just kind of rocket up over the bottom there. And then once we got it vertical, we got the trailer out of the way, and you can kind of see in this view here, we upended it here, and the anchor bolts were right here. So once we got it up, we had to slide the whole thing over before we were able to lower it down on the foundation.
Yeah, it makes perfect sense, and it's also why you said in your previous slide or two why the planning is so important, because to do something like that, you've got to have a tremendous amount of planning to have that ready to even happen.
That's right. And so these drawings are the output, but there's a lot of planning that goes into it. There's structural modeling of the tower. We've got to put wind loads on the tower. We've got to put side loads, because if the trailer is not in perfect sync as it's being upended, it's going to want to kind of push the tower left or right if those load lines kind of get out of plumb. And so having contingency built into the system to be able to accommodate real world
conditions,
inaccuracy. Yeah, exactly. So that's all the engineering that goes in behind the scenes to develop a plan like this.
And what's really interesting about what you do is every job's probably a little different. So it's almost like you have to recreate every single job.
Yeah, everyone is different, and there's a wide variety of what we get into. This kind of shows some of the connection details. So figuring out, specifying bolt sizes, connection types, pin diameters, how everything fits together. This is super critical, because if you get into engineering, especially structural engineering, whenever something fails, 9 times out of 10, it's a connection that fails. It's very rarely do you see just a beam just fail. It's usually a weld or a bolted connection or some little detail that wasn't properly evaluated. So these details are very important in making sure that we're able to execute the job safely. A lot of times we have to build new equipment. So we have to design and fabricate new equipment. So here's an example of a fabrication drawing. This was for a staging beam for supporting that piece that we looked at earlier. So calling out, weld sizes, plate details, where along the length of the beam, everything's going to be installed, speccing that out so we can send it to the fab shop where they can fabricate it.
So you've got like
here's an example.
You've got like a tool and die unit at your place then, right? That can fabricate once y'all design it, that they can build it.
Yes, we've got our own fab shop here in Memphis, and so a lot of once I get into some of these pictures here in a minute, a lot of the red gear that you see, probably 75 to 80% of it, we designed and built in-house. It's not stuff that you go to the market and buy from a vendor. Most of this stuff is specialized to us, to Barnhart.
So tell me real quick, before you go into this, can you kind of tell our kids in your firm the different variety of jobs that exist? Because there's engineers there might be welders there might be, can you kind of describe the different level of jobs, even executives who maybe went to business school? So just for maybe 2 minutes, the job options and what they did in college to be prepared for those job options.
Sure. We've got a lot of engineers in the company that went to college and got an engineering degree. Some of them are still doing engineering like this, but a lot of them have moved on to a different role within the company. So, some of them have gone into branch management where they're overseeing operations. They're overseeing, some of the branches have engineers there, project management. Our senior leadership team, probably half of them have engineering degrees, but they're running the company now. So they're over the business side of things. They're over the profit and loss statements. They're over the strategic planning. What accounts are we going to go to market for, and which customers are we going to target with our services? I mentioned project management. That's another critical role within the company. Is there's got to be someone that coordinates the whole show. I mean, because there's engineering involved, there's operations involved, there's fabrication involved, there's the customer involved, there's permitting that with other state agencies or municipalities. All that has to be coordinated, and so that's the job of the project manager. And he coordinating all that, all the while making sure that the job stays profitable throughout, the planning and execution of it.
Wow. That's a tough job there.
Right. And then sales is another important job. So salespeople you have to have a technical kind of background in order to sell what we do. I mean, it's not like you're a toothpaste salesman where everybody knows what toothpaste is and, who can give me the best price. We're selling a service. We're selling an engineered solution is what we're selling. We're not selling equipment. We're not selling our cranes or our slide system or our gantries or anything like that. We're selling a service. Somebody's got a problem. They need this 500,000 pound generator stator that's sitting in their plant. They need it moved out, and they need the new one moved back in so they can keep producing power and making money. They don't really care what we bring in there. They don't really care how we do it, as long as we do it, safely and cost effectively and on time. And so,
so y'all are literally
being able
paid problem solvers is what y'all are. Paid problem solvers.
That's exactly, yeah. That's why I say I'm a professional problem solver. That's exactly what we do on a daily basis.
That's really cool.
So there's a lot of opportunity, just in Barnhart. I mean, you can go any which way you want. You can stay technical. You can go into sales. You can go into management. You can go into operations. The business side of things. It really opens the door to a lot of different opportunities, depending on what you want to do.
Cool.
So I'm going to kind of speed up a little bit. I think we're kind of running out of time, but this just shows a little bit of.
And Mr. John, why don't we, since we got started a little late, if you want to plan about 10:10, that'll give you a little more time since we didn't get started till about 9:40. If that's okay.
All right.
You have time that's if you have time.
Yeah, no, that's fine. That's fine. So here's some examples of what some of the calculations that we do look like. This one is a ground bearing pressure calculation. So for example, we've got these big cranes that are putting down big loads on the ground. We don't have the expertise in evaluating the ground, the soil for the loadings. And so that's kind of where we draw the line in what is our responsibility and our scope, and where somebody else's responsibility and scope picks up is at the ground. So we have to provide some sort of load spreading underneath our equipment to get it down to a reasonable level that the ground can support. And so we'll provide this calculation, and it shows, under the loadings that we have for the equipment, we're putting down this one looks like about 2,600 PSF, pounds per square feet. And so we'll give this to the customer, and they'll have their geotechnical engineer evaluate the loadings and make sure that the ground is capable of supporting the loads that we're putting down. Wow. And if they come back and say, no, it's too high, then we go back and we sharpen our pencil and come up with some other arrangement to get the loadings down to an acceptable level. Structural calcs. I mentioned a lot of what we deal with is with steel. So a lot of steel design. This is just showing just a generic, I can't tell you exactly what we're looking at here, but it's running through all the numbers. So all the algebra and geometry and trig that you're learning now, we use it every day to evaluate the structures. So a good example of this This is a snapshot of a model that we did for a job, and it's kind of a tower here, and then we've got these beams going in. We got the tower set up outside the building. There's a building in here, and the beams span from the tower over to the pedestal of the building, and so that's what's supporting the end of the beam on this side. And then we had a gantry system that would pick the load and travel it down these beams till we got to the center of this tower arrangement, and then we'd lower the load down onto a trailer, and the trailer would take it out. We'd stage it, bring the new one back in, reverse the process to swap out. It was a generator stator at a power plant in Georgia. So this is the model that we've got the loadings on here. You can see we've got about 200,000 pounds at 4 different locations, about 800,000 pounds cruising across this girder here. That's about I think it was about a 65 foot span from the building to the edge of this tower section right here. So we're spanning over that gap, and we got to make sure all this works as a system, right? It's not just individual components. We have to make sure it all works as one system. You can kind of see the reactions down here to the ground, and in reality, this is what it looks like. So you can kind of see, flipping back, the similarities of our model, versus reality, and being able to model that out and be able to predict how the system's going to respond allows us to really get competitive with our work.
That looks like a nuclear power plant, isn't it?
This is actually a coal-fired power plant, but they have that same type of cooling tower. So you see this style of cooling tower a lot at nuclear power plants, but the coal burners use the same one every once in a while as well.
Gotcha.
The other thing that we get into is stability. And so this particular example is for a crane that we mounted on top of a barge. And if any of y'all have ever been canoeing, that you get a fat kid standing up in a canoe, chances are it's going to turn over, right? But you take that same fat kid and put him on a pontoon boat, he can dance around and get jiggy with it, and everything's good. So there's limits to what you can do based on the loads, based on the height of the CG, the center of gravity, and based on the width of the barge. So we've gone through and developed a set of hydrostatic calculations that allow us to determine whether or not the barge is stable for the loading configuration that we're putting on it. And we've done some testing to prove our numbers. It's one thing to run the numbers, but then there's real life and there's reality. And so everything that we do is backed up with a test to make sure that we haven't missed something, that it's going to be safe when we go out there to do the work. I'm going to try to play this. I don't know how well it's going to work over the internet, but this is rolling on. These are some components from a nuclear power plant up in Wisconsin that these were radioactive, and so there's a lot of planning and extra safety precautions that went into making sure that we didn't have an event obviously being radioactive. But you can kind of see rolling these components onto the barge and how the barge responds as you're moving the load across it. So let's see if this will work. Are y'all able to see it okay?
Yeah, it's coming through.
All right, good.
Is that the new component that you're delivering, or the one you're taking away?
This is the old one. So this one's going to a waste disposal site. And so
that barge,
we rolled these onto the barge, and then barged it down to most of this. I'm not sure where this one went, but there's a nuclear waste disposal site out in Utah. It probably ended up going to there. So we took it from Wisconsin, probably to Catoosa, Oklahoma is usually about as far as you can get on the waterway. And then you have to transload it from barge. It probably ended up getting on a rail car and going the rest of the way from there.
You could see as each piece loaded that barge sunk deeper and deeper in the water.
Right, and you can predict. We can calculate that and predict all that to make sure that, you know, when the ramps go down, that they're not going to bottom out on the edge of the dock, or that the trailers have enough, you know, stroke in the wheel sets to get over there without high centering or floating axles as we're going across that breakover point. Here's an example. This was at the Grand Gulf Nuclear Power Station there in Port Gibson, Mississippi, about 45 minutes south of Vicksburg. This was part of a big project we did back in 2012, where we replaced basically all of the major components within the plant. This was they call it a moisture separator reheater. Basically, it's a heat exchanger. It takes steam from the exhaust steam from the steam turbines and runs it through here, and it heats up the water that goes back to the reactor to help gain efficiencies and just reusing some of that heat and some of that energy that's already been created. But this is the rigging arrangement that we came up with for handling this. This is a 553,000 pound MSR, and in order to get it out of the plant, we had to use 2 overhead cranes teamed up together, and so that's why this spreader beam up here has got a hook location for 2 separate cranes, and it also allows, it's got a swivel here in the middle where you can swivel that piece as you're going through the building. And this is a picture of it in actual use. You can see once there's kind of a hallway back here in the back that we had to work it around, and then once we got past that hallway, we had to turn it 90 degrees like it's shown here before we lowered it down into the truck bay to take it out.
How many of these projects do you work on in a year?
Oh man, you know, we probably work on about 150 to 160 projects a year that engineering supports. Some of them are pretty simple, relatively speaking, and then these can take years of planning before we actually go do the work. But on average, we work on between 150 to 160 projects a year.
Yeah, I was just thinking how long it seems like all this would take from beginning to end, the large projects.
Oh yeah, these, especially in the nuclear power plants, they're so safety conscious that there's so many levels of review that you have to go to. The scrutiny is really high, and so nothing happens fast there. So there's always months, most of the time years of planning that goes into it before we actually execute the work. This is just a screenshot of the program that we use to evaluate our transport trailers, our heavy haul trailers, to evaluate them for both strength and making sure that they're stable. So you're not going to, you know, tip the load off the side of it. And this is a picture of that particular job. We were rolling this one off of a barge, and I think we'd already got it off the barge at this point, obviously, and we were hauling it to the laydown area. This is at a refinery down in Texas, outside of Houston. Mentioned we have to calculate the loads underneath cranes. So this program, we plug in all of our, you know, crane configuration, the weight of the piece, the radius at which we're setting at, and it tells us what our track pressure our track pressures are, and we use our track pressure to determine, you know, the ground loadings that we're putting down on site. So this is the actual job for that one. You can see the crane here, some matting underneath it, and this one we were standing up this vessel here, rocking it over the bottom, and then once we got it stood up vertical, we swung it over and set it on the anchor bolts.
Wow.
This is some more design of specialized lifting beams. So we use, sometimes you can run the numbers by hand, but sometimes you have to get a little bit more detail and granularity in what you're looking at. And so we've got programs, FEA programs or finite element analysis, that allows us to model things as a solid as it is in real life, apply the loads, and you can get in there and see where the stresses are and make sure that the loadings and the stresses are within the capacity of the member. And if it's not, then it's easy to go in there and change things up, maybe make the plate a little bit thicker or go to a higher strength type steel, or change up some of your geometry to make the loading more favorable. But you can model all this and find out and make sure that you've got a good design before you build it and load test it. So this is just one corner of a spreader beam. So if you took it and you mirrored it about this line right here, that's what the spreader beam actually looked like. And so here it is up in actual use up here at the top. This was at a nuclear power plant up in New Jersey, I think it was. These were they call them steam dryers. They're the part right on top of the reactor that the steam goes through, and it kind of dries it out, pulls water droplets out of it before it starts running through all the turbines and components of the power plant. Some of our cool tools. This is a slide system. We've got a few different types of it, but you'll notice the purpose of it is just to slide loads along the length of the beam. So obviously you're going to have to evaluate the loadings on the beam, determine what's the max span you can have between support points, how you're going to support it. But the way it works, you'll notice on the top flange here, there's notches every so often. And you can kind of see it in that picture right there. But what we have is, we call them pusher grippers. And it's basically, we call it a slide shoe. It's another piece that sits on top of the beam. And then we've got two hydraulic cylinders that are attached to it. And they've got we call them dogs. They're basically little notches or little pins that bite into those notches. And once they bite into the notch, you extend the hydraulic cylinder and it shoves the piece down the beam. And so that allows us in a very controlled manner to move loads laterally. If we're lifting things, gantries we use all the time. Basically what a gantry is a big jack. It's a big hydraulic cylinder, and most of the time they're mounted on wheels, where you can install them on a track or a set of beams, and you can motivate the load down the track. So you can raise it vertically, and you can also move the load horizontally along the track. We've got several different types of hoists. We've got a 25K hoist, a 12K hoist. This is our 500-ton hoist that you saw in some of the other pictures. This is our 200-ton hoist, and they all run, just reeved up wire rope back to a hydraulic driven winch or drum. And so we're able to raise loads with that. Strand jacks. These are basically, it's basically a jack, but it's got holes in the middle of it where these strands or wires go through. And there's a set of what we call chucks at the bottom and a set at the top. And what they are is basically wedges that bite into the strand and hold it. So the harder you pull, the more it's driving that wedge into the little hole that it's seated in. And the bottom chucks hold it. The jack strokes up, and so you're able. It's holding the strands and the load that is connected to. It strokes up whatever it is, 2 or 3 feet, however much stroke the jack has. Then once you get to that point, the top chucks grab it, and then the cylinder retracts. And then once it retracts, the bottom set grabs it again, and then the jack pushes it up again. So this is something that you get a lot of capacity out of, but they're really, really slow, and it takes more time to set them up. But sometimes they're the right tool for the job. I mentioned the Goldhofer trailers. Those are the platform trailers that we use a lot. You can use them in bolster type configurations like we're showing here, where you've got two separate trailers where they're able to steer relative to one another. They're more maneuverable. And then we've got self-propelled, where it runs off of a remote. There's an operator walking behind it and controls the steering and the forward and back and leveling of the trailer from a kind of a remote console. And then we've got some truck pull type trailer that it functions the same, but instead of being self-propelled, you have to hook a big truck or a prime mover to it. This is our tailing device. And what this allows you to do is, like I showed you in some of those other pictures, you can upend vessels and you don't have to have a separate crane, a second crane, to handle the tail end of the piece. You can just use one of these Goldhofer trailers and just rock it up. And so you can see it starts here, it pivots about this point, and then when it gets to a certain point, this pin engages right here. And that is a very critical detail to figure out, because if you've ever taken like a Coke can and tried to rock it up from horizontal to vertical, at some point it's going to flop over when that CG gets past the pivot point. And when you're picking, 500,000 or 600,000 pounds, you don't want anything flopping over. You want to control it the whole way. And so you can do that by just introducing a new rotation point right here that forces it to, keeps the CG on one side of the pivot point the whole way throughout the upending process. We got a modular tailing tower. Again, kind of the same thought as the other one. It just eliminates having to have a second crane to handle the back of the tower, or back of the piece that you're lifting. And the way it works is you hook it up to it, and then it just slides down the track here as it's being upended. This is our dolly rig. This is another very custom transport rig to allow big loads to go over the road. Again, the name of the game is just spreading the load out. So the heavier the load, the more wheels you're going to have to put underneath it. And the more wheels you have to put underneath it, obviously the bigger and the longer it's going to get. And so you have to really get creative to be able to figure out how you're actually going to make the route, be able to, make the turns and be able to get it to its final destination.
Literally drive it from one place to another. You got to think of how you're going to get across that highway. That's
right. That's right. And sometimes we have to get the customer to come out there and fill in the median. This one, you can see they've dumped a bunch of rock in here and compacted it because there's an overpass up here that it couldn't support the load. So we had to get off the highway, get off the off ramp, cross the median, and come back on the on ramp on the other side in order to go around that bridge that couldn't support the loads.
Well, and a couple of things there. First, you have to evaluate every bridge you drive over. And second, you had to get whatever permitting you could to shut the freeway down for that moment of time.
That's right.
Yeah, man. I can't imagine the amount of the size of the team it would take for these projects to be a reality.
Yeah, it takes a lot of coordination, a lot of different people, all knowing what their roles are, what their responsibilities are, and everybody doing their job. Here's some more MLT jobs. This was the big tunnel boring machine up in Seattle. We did, 5 or 6 years ago. The heaviest lift we had here, this whole tower, you can see it's got strand jacks doing the lift, and this whole tower could slide back and forth on some of those slide beams that we were looking at before. So there's a launch pit, and so you bring the components in front of the launch pit, you lift it up, and then slide the whole tower back and lower the components into the pit, and you're building out this tunnel boring machine that basically, I think it's open now. They've rerouted a viaduct or roadway underground underneath Seattle. I think the heaviest lift we had there was about 1,200 metric tons. Here's an example of, I mentioned accelerated bridge construction. This is one that we did up in Connecticut back in 14. Man, it's been 6 years already. This was a 2 million pound bridge. And so you can kind of see here, We've got our Goldhofer trailers with kind of a stack up of girders on top of it. And then you can see we've matched the profile of the bridge with our beams and kind of cribbing on top of here. Because when you're in a curve on a highway, the road, they call it super elevated. It's slanted to one side, so you can go around the curve faster without flying off the edge of it. And so that's something that that's another detail that we have to accommodate in our planning. But you can see we just cruise in there, we lift it up. You can see we've got some jacks on top of the trailer, between the trailer and the girders. We're able to stroke those up and get another 60 inches worth of vertical lift to get them up and off the abutments. And then we travel it back to the staging area. We'll set it down on shoring towers, pull back in underneath the new one, and reverse the process and set the new one in place. There's a YouTube video. I won't waste time showing it right now, but I'll send you the link, Robert, and if you want to share it with your students.
Yeah, that'd be great. Share it with me.
This was the actual job. I was showing you some of the project drawings at the beginning of the presentation. This is some pictures of that job during erection and during the lift. I'll show you a quick time lapse of the actual lift on this one. There we go.
When you ride by something like this, you never think about how did that get there. And I'm sure that you think about it because of what you do for a living. But now every time I ride by something like this, I'm gonna be thinking, how in the world did they get that there?
Yeah, you do have a different perspective on things now. Again, this was a 200-foot tall lift tower we did down in Texas, lifting up in a 600,000 pound component. And so this is the other cool thing about this job. I mean, there's not many jobs where you're going to climb 200 feet. I mean, there's ladders on each one of these legs of the tower. You can kind of see it. This is the climb that you get to make, and there's some pretty cool views once you get to the top. But again, very cool job. Here's a quick time lapse of that lift. This one was kind of tricky. You can see it was pretty windy out that day, and we had a bunch of clouds that kept blowing in on the tower, so you weren't able to see the piece half the time. But the winds were blowing about 25 miles an hour, and so we had designed it to a 30 mile an hour to be able to sustain a 30 mile an hour wind during lifting operations. It could handle more unloaded, but if we had the load on the hook, we could safely lift up to 30 miles an hour. But when you get up to the top and the wind's blowing like that, the whole tower's swaying. And it's swaying about 2 feet, which can be kind of unnerving. But if you've done your numbers right, and that's exactly about what we were predicting. So it's pretty cool to be able to see how, if you do it right, the math really does work, and it really is helpful.
Well, and also did you have somebody on site monitoring the winds? That way, if it did get over that 30, they would shut it down?
Yeah. And so, I mean, I was on site for that job and serving as the risk manager. And so that's one of the functions, is to make sure that, we're operating within the correct parameters. So we had anemometers mounted on the crane next to it that was, catching the wind speeds way up there at the top. We had a transit there. We were able to measure the load line to make sure that when we were standing up that piece, we were keeping that load line plumb and we weren't dragging the tower one way or the other. And so, as the engineer, you know where the critical aspects of the lift are. You know what the critical pieces of the system is. And you're able to be out there on the job and make sure that everything is done in accordance with the plan.
Mr. John, I just really want to thank you for doing this. I know your time is valuable, but it's neat for the students to be able to see the math that they're learning now you see people all the time on Facebook say, well, I went another day without using algebra. Well, that's not true for you.
Right.
You probably use it most every day. So it's neat for the students
every day. Yeah.
Well, it's neat for the students to be able to see all that math that they're learning, because there are some students on here who enjoy problem solving, who I could see become an engineer. And so they're getting to see a real world use for all the work they're doing right now in school.
Yeah. It's definitely, stay in school. If this is something you're wanting to do, pay attention in math and in science, because there are definitely jobs out there where you're going to rely on it heavily, and we use it every day, and we wouldn't be able to do this work if we didn't know how to do it. So,
well, thanks again for joining us, and we really appreciate it.
Absolutely. My pleasure. Y'all have a good day.
Okay, you too.
Bye.